Welcome back to another exciting chemistry lesson. In the previous lesson, we learned how to find rate law using the experimental data of that chemical reaction, and we also learned how to use the data to determine the order of each reactant in the rate law. Now, we also learned that in most chemical reactions, it would involve multiple steps. Okay, now this is what the lesson is going to be about. The multiple steps that are involved to make a chemical reaction. So most reactions that you see involve more than one steps. And these steps are known as elementary, think of basic steps, okay? They are elementary steps or elementary reaction of the overall chemical reaction. Now, again, we learn how to write the rate law of the overall chemical reaction using experimental data in order to determine the orders of that particular reactant, right? But in the elementary reaction, and when we are given an elementary reaction, all we have to do is look at the coefficient, but there is a catch which we will look at carefully. So all we have to do is look at the coefficient of a balanced chemical equation. So let's look at the three common types of elementary reaction. First, you have unimolecular. Think of uni is the prefix for one, okay? So we just have one reactant decomposed. As you can see here, we have a K constant. Then we have bimolecular. Think of bi as in two reactant collide. So in this case, we have A and A. This can be rewrite as 2A, right? That coefficient is 2. And we have A and B. You can see that we just look at the balanced chemical equation. So this coefficient right there is right there. Now let's look at termolecular. Of course, this could be more than 2. So every time we have more than 2 reactant, we have termolecular, okay? More than 2. So let's look at this. We have 3A plus A plus A. Well, that is just 3A. See how this is the coefficient right there? Here we have A plus B. Well, this can be right as 2A as well. So sometimes they don't write separate. In most cases, actually, they would write it together. So as you can see here, that's the coefficient right there. Or we have A plus B plus C. You can see that right there. Now, the speed of the overall reaction is determined by the slowest steps. And that makes sense, right? The overall reaction cannot go faster than the slowest. So the speed of the whole process cannot be faster than the slowest steps. And that's why we focus on the slowest step. And that slowest step is the rate determining steps, which we will also learn that is also the rate law for the overall reaction as well. Now, there is a catch. We have to look at this right here. There are two conditions that we need to qualify for. First of all, the reaction mechanism where the elementary step need to be irreversible. What does that really mean, irreversible? Well, that is going in one direction. This right here is reversible, okay? Or you can see that like that sometime. That is reversible. This right here is irreversible. Or in which the first steps is the rate limiting. Well, think of that, rate limiting. That is basically saying the first step is the slowest steps. When we have either condition are met, the rate law of the overall reaction is set by the slowest elementary step, which is given to us, or the rate limiting step. So let's look at an example problem and see how it works. First of all, we have this chemical reaction divided into step 1 and step 2. And you can see right there, it tells you which one is the slowest steps, or slower, right? So in this case, both of them are not reversible. And the first one, it is the slowest. So we have two conditions met as well. Not just one, but two. So the rate law is very straightforward. Rate equal to always the K constant times the reactant. In this case, we don't have any coefficient, so we don't have to worry about that. 0.3. There you go. And that's all you have to do. Isn't that easy? Now let's try another problem. Here we have the same thing. Both of them are not reversible. And the first one is the slower one. So there you go. The rate law is just rate equal to K times the constant. Oh, look at that. We have the coefficient. So we have NO2. Okay, there you go. See, this is that part. But on our computer, we are going to write like this. NO2. There you go. And that's all we have to do. So please take the time to memorize this information. Right? This is extremely important. Because in the next video, we are going to look at different situations. What happened when it is reversible? And what happened if the first steps is not the rate limiting step, and it get the whole thing changed a lot. Okay, so as always, if you have any question, take a picture of your work and ask us right away if you can. And we'll see you next time on another exciting chemistry lesson.